The width of a river is d equals 90, so 90 meters. Okay, so I'm going to just do 90 right there. The water flows with a constant speed, vwg. So I think this is speed of water with respect to ground. With respect to its banks, an athletic swimmer can swim at a speed of 6 meters. That seems really fast. That's like 12 miles per hour. 6-minute mile? That is quick. So velocity is speed with respect to water in still water. Although she heads directly across the river towards the opposite bank with her maximum effort. Maximum effort. She arrives at point C on the opposite bank at a distance L, so 60 downstream. Okay, and I'm going to do a little V here for 6 meters per second. Okay, speed of the water relative to the ground is, and then we have, okay, so what we got here is we have water flowing. This water is pushing the swimmer. We're assuming that it's pushing it perfectly, and we're trying to find out how fast this water is going. So the idea here is she swims this way, but their combined vectors goes that direction. So what we have here is, so there's a couple ways of looking at this. We're going to look at with the kind of brash, winging it type methodology. So this is going to be a case of similar triangles. And so our triangles would be 90 meters, 60 meters, 6 meters, and then we'll call this X. Yeah, that's good, X. And then, so it could be like, well, 60 divided by 90 equals X divided by 6. Rearrange this. 60 divided by 90 is 2/3. Multiply by 6 equals 4. Whoop. Equals 4, which will equal X. So this X value here will be 4. The reason that works is because when we have our kinematic equations, we have A equals A, V equals AT plus V naught, X equals 1/2 AT squared plus V naught T, whoop, move over a little bit, plus X naught. In this case, we have 0 acceleration, so that goes away. We assume that X naught is 0, and so we're left with our equation of velocity equals distance divided by time, which is pretty much what we're used to, and it gives you this, I guess, linear relationship between distance and time. So that's why this sort of similar triangles method works here. Now, a more methodical way to look at this would be to think of it in terms of, erase this, get rid of that. So we have a distance that we're going to cover here of 90 meters. So we have 90 meters. We want to find out how long it's going to take to get across that. So she's swimming this direction, and all she cares about is facing the other bank, and she's going at 6 meters per second. So divided by 6 meters per second. Look at this in terms of unit analysis. This is the same as 90 over 6, and then this will be meters times seconds per meters. What I did was I was dividing by the fraction meters per second. So when you divide by a fraction, you multiply by the reciprocal, which is seconds over meters. This cancels, and you're given 90 divided by 6, which I think is 15. Probably should check that. Whoop, clear. 90 divided by 6, 15. So we have 15 seconds to get across the river. So if it's taking 15 seconds to go across the river, we also know that she goes 60 meters, I guess, downriver, and she's doing that for 15 seconds. So let's see. We're trying to look for a speed, so we'll divide by. This is just complete dimensional analysis. I'm not remembering any formula for this. For this, I'm just saying I want a speed. Speed is measured in meters per second. So if I have 60 meters divided by 15 seconds, then that will give me some answer in meters per second, which is a speed. So this will then also give us 4 meters per second. So that's a more rational way to work through it. And one of those things, it depends on how much time you have. If you feel like you're keeping pace and you're keeping on track on where you're supposed to be on the exam, then go through it as slow and methodically as possible. But if you're kind of panicking, don't have a lot of time, you can kind of look at this and be like, wing it. So this answer, the speed of water with respect to ground will be 4 meters per second. Okay, so the next part is, if instead she chose a heading that would get her directly across the river, straight to point B, how long would it take for her to get to the other side? Okay, so now that we know the speed of the water, this is just adding vectors. So we have, this will be velocity of the woman with respect to, I guess, water with respect to ground. No, that's not what we want. We want the velocity of the swimmer. Whoop, there we go. So, I can go with this. So I'm going to speed swimmer. And so this can be broken down into two components, Vx and Vy. And we know that this Vx portion is going to be 4 meters per second because the velocity of the water is 4 meters per second this direction. So when you add them together, you're going to have something that looks kind of like this. This is velocity of the swimmer. This is velocity of the water. And therefore, their net, when you add them together, will look like this. And this is what we want, straight from point A to point B. And so, let's see. If instead she chose, how long would it take? Okay, so we want to find this angle theta right here. So the way we're going to do that is we know that velocity swimmer, I know I'm changing up the notation, I'm fine with that. We have SOHCAHTOA. So we're going to use opposite over hypotenuse because we know something about the Vx. So velocity swimmer is the hypotenuse. Opposite over hypotenuse over Vx equals sine theta. So sine theta equals opposite over hypotenuse. Opposite over hypotenuse. There we go. We know Vx, that's going to be the 4 meters per second. We know V swimmer, that we were told was 6, which is still very impressive. 6. And we're trying to find theta. So theta equals arc sine of 4 divided by 6, which I'm going to call 2/3. And then theta gives us, mode, click, click, degrees, second quit, second arc sine of 2 divided by 3, there we go, 41.8. 41.8. Check that to make sure I didn't go crazy. Nope, 41.81. I'll say 81. Okay, 41.81 is our theta. So now if we look at our triangle again, we have 6 over here, and this theta is 41.81. And we want to know what Vy is. This is the speed of the swimmer directly across the lake. That's going to give us, let's see, go back to our SOHCAHTOA. We're now going to use cosine of theta equals adjacent over hypotenuse. So cosine of theta equals adjacent over hypotenuse. We're looking for adjacent here, which is this one right here. So we have 6 times cosine of theta equals adjacent. Going to our calculator. Let's do 6 times cosine, second answer. That way I get to keep the whole thing. That should give us 4.47 equals 4.47, and that's meters per second. So that 4.47, we're going to be using that to cross 90 meters. That's actually a pretty big river. 90 meters. That is a big river. So we'll do 90 meters divided by 4.47 meters per second. Meters will cancel. And so this is going to give us a time. So we'll do 90 divided by, oh, that's a 4. 4, there we go. So we'll do 90 divided by second answer, and we get 20.12. 20.12 seconds. We get our possible answers. Boom, boom, boom. 20 seconds right here. So to backtrack what we did here, we were trying to find if the swimmer at this time swam at an angle so she went straight across. The other way of saying that is the x component, or the component that's along the same direction as the river, from the swimmer will cancel out the flow of the water. And so I think that's called a crab angle. Is that called a crab angle? I think it's called a crab angle. Goes straight across the river. And so we're basically given what the Vx is of a triangle. We use that to find the theta of what this triangle would be, this angle. We then took that angle then and used that to find the how fast she was actually going to cross the river. We knew how long the river was, and so we took this speed and this time, or this speed and this distance, and then converted it to a time. And that's how we found out how fast she went across the river. So this did take a little bit while. You can go through this, if you're on a test, try and go through this a little bit quicker. I tried to explain a lot. I went a little slower, but this is, it's a good problem. Good question. All right, on to the next one. A ball of mass m equals 1.5 kilograms is suspended from a rope of length L, as shown, and travels in a horizontal circle of radius r equals 1.8 meters. That's a big circle. At a constant speed of 4 meters per second. That's a good speed. As shown in the figure. What is the horizontal component of the tension in the rope, in the rope T horizontal? Okay. So, looking at this tension here. So we got this tension coming up at an angle. This can be broken up into T, I'm going to call this X, which is the horizontal, and T, Y. Might not be fair to call it TX and TY. Maybe it's supposed to be TZ. I don't know. You see where this is going. So we're trying to find the horizontal component. So the reason that horizontal component is going to exist is it's going to be offsetting the centripetal force pushing it outward. Pulling it outward? Not really sure. So the idea, though, is, let's see here. So centripetal acceleration equals v squared over r. Therefore, force centripetal will be mv squared over r. There we go. You just have to remember that v squared over r is centripetal acceleration. The mnemonic I use is that centripetal acceleration is the same as electrical power, where a centripetal equals v squared over r equals v squared over r, which equals power. Now, I like this because it's a terrible misconception, gross conceptual error, if you will, because these are volts, that's resistance, that is radius, yep, and that is speed. So even though the letters are technically the same, that is a gross conceptual error, and it's just so absolutely wrong that it helps me remember it. It's funny how you always remember the bad ideas. But that's just my mnemonic in life. You can use whatever you want to memorize that. Centripetal acceleration is v squared over r. So this is going to be equal to tension in the x direction. Yep. Because we only have three forces going on here. So we have gravity, which is going to be perpendicular to the x direction, so that's not going to affect it. And then we have tension. Yep. So Tx will be, let's see here, mass 1.5, speed, which is 4, that'll be squared. And then we have the radius, which is 1.8. So this will be like, what, 15? 15 probably. Okay, so 1.5 times 4 squared divided by 1.8. Let's do this. 1.5 squared. No. 1.5 times 4 squared divided by 1.8. 13.3. I guess it's a good thing I didn't estimate that on my own. I would have been way off. Well, at least way off enough to get the wrong answer. And this is a tension, so it'll be in newtons. So 13 newtons. Okay? What is the length of the rope? Interesting. Okay. So I think what we're going to have to do, so we're going to draw this tension out here, and we're going to break it up into its components. So we have tension going up that way. We know that it's 13.3 in this direction, and we can also find the tension in the y direction. Tension in the y direction, Ty, will be mass times gravity, because it has to cancel out the gravity. So centripetal acceleration is outward horizontally, mass times gravity is down. They're perpendicular, so we can draw them as a triangle. They don't affect each other. But the tension, it'll account for both of them. And since those are the only three forces in play, we know that's all that's going to be accounted for. So mass times gravity will be 1.5 times 9.81, and I'll go with 9.8. Let's see here. 1.5 kilograms, 9.8. Yep, I'm good with that. So let's take, what, 15? 1.5 times 9.8. Maybe 14.7. 14.7. So 14.7. We can now use this to find this theta here. So theta. So we do SOHCAHTOA again. I do love SOHCAHTOA. I didn't learn that until college. I wish I learned that in high school. So useful. Okay. Tangent of theta equals opposite over adjacent. So opposite will be 14.7. Adjacent will be 13.3. Therefore, theta equals, Come over here. Second arctangent of 14.7 divided by 13.3. I think I'm still in degrees. So I'm going to say 47.86. Check to make sure I'm right. Yeah, close enough. Okay, so now that we have that, this is going to be the similar triangle to the lengths of, because it's the lengths that determine these proportions. So we're going to have a radius of 1.8. This radius is right here, 1.8. And now that we know the angle, it's a right triangle, and one of the sides, we can figure everything out. In this case, though, we want to use, let's see, we have adjacent and we have hypotenuse. So cosine of theta equals adjacent over hypotenuse, so 1.8 over, I'm going to write this as L, because that's what they use in the problem. So therefore, L equals 1.8 over cosine of theta, where we know what theta is. So let's do 1.8 divided by a quantity cosine second answer, close parentheses. We should get a number that's bigger than 1.8. So 2.68. 2.68. See if we need any more. Let's say 2.9. 2.6829. That's probably measured in meters because it's a distance. Aha. I'll go with this one then, right here. 2.68. Oh, that's how we do that. To backtrack a little bit, how we did this problem was we were first asked to find the horizontal component of the tension. We know that the horizontal component of the tension is just offsetting centripetal acceleration, which we know by the formula acceleration equals v squared over r. So we then were able to find the horizontal component of this tension. We then tried to find, or we then found the length of the rope. And we did that by making a triangle of the tensions. So we had centripetal acceleration on the horizontal. We had mass times gravity on the vertical. And that was the vector component breakdown of the tension. And so from there, we were able to find an angle. We used that angle to draw a similar triangle, and then use the radius of the circle we're making to find the length of the line or the rope. Man, that was a long explanation. Too long. So, hope that made sense and it kind of intuitively followed through. Usually when I start these problems, I don't know where I'm going. I just see what information is given to me and I kind of fumble my way through. So you're like, wow, this guy's really smart. He knows all the right steps to make. It's like, no, I don't. It's usually I'm making a lot of it up as I go. And just because you start somewhere doesn't mean you know where you're going to end up. Which, not ideal, but I guess in the grand scheme of things, life isn't ideal. Okay, on to the next problem. For the following problems, assume the Earth is a sphere. Okay, I think that's 6,400 kilometers. Yep. And mass of Earth is 6 times 10 to the 24th. I think the sun is about the same, but times 10 to the 30th. So, okay, seems reasonable. Person weighs 120 pounds on the surface of the Earth. How much would the person weigh on the surface of a planet that was 1/2 the mass of Earth, but also 1/2 the radius? Okay? So, we're going to do force of gravity equals big G, mass 1, mass 2 over r squared. And we're going to say that force 1 equals some sort of constant, I'm just going to call it alpha, times force 2, where this will be Earth, and this will be not Earth. And so this first one will be G, mass 1, mass 2 over r squared equals some sort of constant times G, and then this will be the mass of the person over, I'll call this mass person? Maybe. How much would the person weigh? Okay, so weigh, this is asking for the force. So the mass of the person stays the same. So M1, which is I'm going to call the person, will be the same. Mass 2 will be Earth, but that'll be 1/2 now. And then the radius will be also halved, but we have to square that 1/2. I know, it's so sideways. Okay, so we cancel out the gravities, cancel out the masses. And so we have mass 2 over r squared equals mass over 2. Instead of dividing by a fraction, I'm going to multiply by the reciprocal, which is how you divide by fractions. So we'll have r squared on the bottom, and we'll have 4 on top. The 2 and the 4 cancel and gives us 2. Oh, can't forget the alpha. Do some more canceling. Mass 2's cancel. R squareds cancel. We get alpha equals 1/2. So we have left 1 over here. Yep. So alpha equals 1/2. So we're going back to the beginning here, where this is the force of the person on Earth. This is the force of the person on the other planet. And we're trying to find the how much the other person will weigh on the other planet. Weight is a force. So here then we know that. So F1 equals 120. I'm going to write this as lbf, pounds force, as opposed to lbm, which is pounds mass. Pounds can be used as a force or a mass. Traditionally, it's used as a force. lbm is generally used when you're trying to specify it as a mass, which is not as common. But I like to specify all the same. Times 1/2. Okay, wait a sec. So F1 over alpha equals F2, which is what we're trying to find. So we have 120 divided by 1/2, which will be 240, which is the force on 2. There we go. So the weight on this not Earth will then be 240. 120 divided by 1/2, which kind of makes sense because mass does not decrease linearly. So if you have a, does that make sense? Maybe it makes sense. So if you have a, the density of the planet would stay the same, because as you're decreasing the radius by 1/2, there's an r cubed relationship in there, not a 1/2 linear. I don't know. There's something else going on there. I shouldn't. Yeah, I'm not going to go into that. Okay. So 240 pounds, and that's how you find it. Poop, poop. So you might be able to just reason this out, but because the answers are, more, less, or stays the same. It's probably not going to stay the same. Maybe it does. This is the way you should approach it. Poop, poop. Okay. Sounds reasonable. Get rid of this guy. So now we're looking at what is the speed of a 128 kilogram satellite in a circular orbit around the Earth at a distance of 1.92 times 10 to the 7 meters, which is bigger than 6.4 times 10 to the 6 meters, which is good, means that it's actually above the Earth. But this is respect from the center of the Earth. Okay, what is the speed? Circular orbit. Okay, so circular orbit means centripetal acceleration. So we'll write up that centripetal acceleration equals v squared over r. Force centripetal will be mass times acceleration centripetal, which will be mv squared over r. And we know that this will be offset by force gravitational, because it's centripetal acceleration is throwing it out. The force gravity is holding it in, and this is the whole idea of how we get orbits. So force gravity will be g mass 1 mass 2 over r squared. So we look at this part, we look at that part, and what we're trying to find is that v right there. So solving for v, we have v squared equals g m1 m2 over r squared. And this will be m1, because that's the thing that's being flung around, times r up top. Get out a canceling color. So the r, one of the r's goes away, m1 goes away, and we're left with a gravitational constant times m2 over r. Seems reasonable. So now I need to know what g is. So we go to Wikipedia. We'll do a gravitational constant. There we go. Ooh, gravitational wave. 6.67 times 10 to the negative 11th. That's the SI units. So 6.67 times 10 to the negative 11th. 6.67 times 10 to the negative 11. Make sure it's 11 in. Yep, okay. Times the mass of the Earth, which is m2. 6 times 10 to the 24th. 6 times 10 to the 24th. Probably can make a bigger parenthesis there. There we go. Divided by the radius, and this is going to be the radius of the satellite orbiting from this as respect to the center of the Earth. So 1.92 times 10 to the 7th. 1.92 times 10 to the 7th. Okay. So now we're going to do some canceling. I like to do the canceling before I put it in my calculator. I feel that it reduces the number of errors. So here, this is going to be 13. So 24 minus 7 is 13. 13 minus 11 is 2. So we have 10. Let's do it this way. Start from the left. 6.67 times 6 times 10 squared, which is just going to be 100, all over 1.92. That feels like a small number. Wait a sec, that's not 13, that's 17. So 17 plus 11, that'll be 6. So we have 10 to the 6th. That seems more reasonable. think so. 24 minus 7 is 17. 17 minus 11 is 6. Okay. Whew. So my belief is that the goal is not to make mistakes. The goal is to be able to catch your mistakes when you make them. Okay. Whoop. On. Clear. Oh, it already cleared. So we'll do 6.67 times 6 divided by 1.92 times 10 to the 6th. Second square root, second answer. We get 4565. 4565 meters per second. Whoop, whoop. Let's see how that compares. And right here, I think this is going to be the answer I'm going to go for because it's close. So what is the speed of... Yep, that's the closest one. That one's pretty close too, but we're going to go with 4565. What is the speed of a 128 kilogram satellite? The mass doesn't matter of the satellite. In a circular orbit around the Earth at a distance of that. So the mass does matter for centripetal acceleration, but it also plays into the gravitational pull. So they cancel each other out. That's why we ended up canceling out our mass ones over here. So the idea here was we set our centripetal acceleration equal to our gravitational acceleration. And that gave us an equation. We solved it for v squared, which we then square rooted. And after square rooting it, we got 4565 meters per second. Okay. Hope that helps. I will see you next time.